Thank you, Nick, so much for the nice introduction. So welcome to my talk, everyone. My name is Philipp. As Patrick just mentioned, I'm a PhD student based in Germany. We are both affiliated with the Cultural Institute of Technology. And basically, my research areas are focused on how you can utilize machine learning systems or AI systems in order to retain expert knowledge, but also to distribute expert knowledge within organizations, to basically convey this expert knowledge to let's say, new employees and so on. So within this, my research is mainly focusing on explainable AI, how you can make use in what we call in this presentation machine learning based teaching systems, how you can utilize explainable AI to basically transfer the kind of expert knowledge. And when I started with my PhD, we're basically interested in, okay, well, out there are so many different kind of teaching constructs, teaching phenomena, and we kind of wanted to conceptualize in the first step, actually underlying constructs, elements that are important in order to define such machine learning based teaching systems. We kind of wanted to synthesize the meaning of machine learning models within such systems, and also understand the role of explainable AI, how explainable AI is used in such context. And this is basically how this project that I'm going to talk about got established. This is based now, the presentation is based now on a paper that I will present at CCW this October. And I would also like to shout out to my co-authors, Niklas Kühl, Daniel Heinz, Gerhard Zapke. Niklas and Gerhard are my supervisors here in Karlsruhe. And it was really nice working together on this project. Cool. So whenever you have questions, just feel free to interrupt or raise your hand. So I actually like to start this the topic normally with a short example, an example of chess. So you basically kind of get the idea that was underlying our thoughts and our progress here. So imagine you are playing chess, and I actually started playing chess like 2 years ago, and I always played against my best friend, and I lost almost every single game, mainly because I was just bad. I didn't know any good strategies. And then I started using such chess platforms like Lichess or chess.com. And it was actually super surprising how good those platforms are already set up. You're getting like good advice. And then I dig a little bit deeper also in terms of this project here, and realized, okay, actually what's underlying is some kind of AI system that is giving you recommendations and explanations how you can improve your chess game. And this basically kind of explains the idea that we had in mind when we started with this. Because what's happening is that in the beginning, those AI systems were trained on past human decisions. So basically, we just had a lot of data where we looked at all those grandmasters that did fantastic chess moves, and we tried to kind of train our machine learning models based on those past decisions that those humans did in the chess game. And then, of course, by the time, as you all know, also we kind of utilized in reinforcement learning. Those AI systems got better in the chess games. They even surpassed then human performance and actually beat all the grandmasters. But that's not the point right now. But the point is that at one point then, those AI systems got actually then set up in a way where they were then able to kind of transfer the knowledge that they incorporate back to the humans. So basically, those AI systems started as kind of a learner. They were basically given all the knowledge from the experts. And then they turned around and actually taught humans like me that were super bad at chess. And it's kind of nice. And the figure here on the side should illustrate what's going on. So basically, whenever you're doing a chess move, and let's say you're playing against the computer, and you're doing a move that is like not optimal, or I actually don't want to use the word optimal, but a move that basically could be improved, right? The AI is basically giving you recommendations on where you should actually play your figure. But besides giving you this recommendation, it also gives you an explanation what's happening based on your move. And this is basically the underlying idea that we use such AI systems and also use explainability and interpretability methods in order to advance this kind of knowledge transfer. Okay, cool. So I hope with this, the overall idea got clear. And now I would like actually to lead you through this presentation. I'm first gonna give you a short introduction, how we basically started with this conceptualization and how we established this framework. Then a little bit on the methodology, how we did it, and then I want to focus on the results and basically also leave some time for a short discussion. Okay, so I mean, why is it so important that we actually look at this kind of knowledge transfer, and why is it actually important that we, instead of utilizing machine learning models in the conventional way, so basically where they're taking over tasks or some other processes, and now basically look at it from an angle where we utilize those models so they actually teach humans in specific domains. Well, this is especially important because training of employees, especially in organizations, is super important. So those organizations can maintain their long-term success. And traditional methods normally lack a lot due to that they're super cost and resource expensive, but I'm going to talk about that in a second. And so in such organizations, we have like a lot of experts, but nowadays you maybe heard of the term baby boomer generation. We actually living in a century where there are about to retire a lot of those experts. So there's actually a high risk of knowledge loss that such organizations try to prevent. And then, of course, we're also having human resource bottlenecks. So we're not only having those experts retire, like this baby boomer generation aspect I was just mentioning, but there are also a lot of human resource bottlenecks. And what I mean with that is, right now, like people are switching their jobs way more often. There's a war for talent out there. And this means that people are basically transferring between organizations all the time. And of course, what organizations try to maintain is, well, what those people had in their heads, in their minds, so their knowledge. And then, of course, we have those conventional methods, and conventional methods are things like, okay, well, we have human-based learning, so where we actually take experts and then place them next to, let's say, new employees or novices, and then have them train those experts. We also have like conventional knowledge management systems, like, I don't know, Wikipedia articles, documentations, and so on. But in those, you cannot store all the knowledge at hand. You can only store the explicit knowledge. And now I was just mentioning explicit knowledge, so I quickly want to dive a little bit deeper into what knowledge actually is, what kind of different forms of knowledge are out there. So normally what we differentiate are explicit knowledge and tacit knowledge. So whenever I refer to explicit knowledge, I basically refer to knowledge that is transmittable, that can be somehow explicated in your natural language. So you would be able to write it down, you would be able to store it in documentation. And traditional knowledge management systems, they can do that. But what they cannot do is they cannot like explicate your intuition, your expertise that you basically collected over years of work and experience. And here comes the big advantage of AI systems into game. We can utilize AI systems and we can utilize explainable AI on top of that in order to foster this kind of knowledge transfer. And this is basically what we're trying now to conceptualize as machine learning based teaching systems. So to sum it up, conventionally, when we look at human-based learning, we had this direct flow of knowledge transfer where we have the subject matter expert that is normally like an expert in a specific domain that, for example, is giving advice, is giving instructions, examples to a novice. So the novice learns. We can kind of think of apprenticeships where novices basically kind of like look over the shoulder of subject matter experts. And in machine learning based teaching systems, basically we have this indirect knowledge transfer where we first have our subject matter expert. We have some knowledge transfer to a machine learning model, to a machine learning based teacher. And then from this teacher, we have the knowledge transfer to the novice. But we have a lot of a lot of advantages when we look at it from this angle, because we are more generalizable, and we are way more scalable, because we don't have to set up experts, human experts, for such kind of tasks, and they can instead focus on like more cognitive heavy tasks. Okay, so with this, what we basically did we basically tried to scrutinize, okay, what is actually out there. So there are so many different kinds of ways how people describe such teaching systems. We have machine teaching, we have intelligent tutoring systems, we have e-learning, and so on. So we wanted to understand, okay, what is actually the role of machine learning and explainable AI within this context. And that's why we conducted a inductive analysis. Basically, we first started with a literature review and then tried to develop a framework based on that. So our literature review, we basically based on a paper from Wolfswinkel. And what we did is we started to sample data by looking at literature with specific search terms. So we basically looked at machine teaching, machine tutoring, intelligent tutoring, and so on. So to basically derive an understanding what's out there. And we searched several databases like ACM Library, Web of Science, and Scopus. And then we read through the articles and titles through the abstracts and titles in order to kind of find out which are actually the important articles that we need to focus on in order to create this understanding. So then we screened the full text. So we ended up with 21 articles. And based on those 21 articles, we then started our data analysis. So, and we kind of were inspired in order to develop this framework based on Choya. So I'm gonna like lead you through what that means and how this is set up. So what we did is basically we started to code those 21 papers independently within the author team. So basically we were 3 researchers that independently performed 3 kinds of coding styles. I can outline in a second what those coding styles are. And based on this understanding and on the discussions that we did, we kind of also screened a little bit forward and backward those articles, and then actually came across 8 more articles that we figured are super important in order to kind of utilize what machine learning based teaching systems are. So based on those 29 articles, then we conducted several coding workshops. And in those coding workshops, we basically went through in an iterative way. So first we try to understand, okay, what are actually underlying constructs, then we try to link those constructs together and try to understand their meaning and put it in the context of machine learning based teaching. So how this actually looks like is, you can think of it like this. On the left hand side, and I don't want to bother you with too much theory, but I think it's super interesting because for us it was a super helpful guideline in order to kind of understand what are the underlying phenomena that basically are described in literature so far. So as I was just mentioning, based on the open coding, we were able to construct those first order concepts. So basically here we're having like 3 different orders, first order concepts, and those first order concepts are based on the open code. So where we basically went through the articles independently of each other, and then in a workshop sat together and tried to align on our understanding. And then based on this understanding, we went ahead and tried to come up with themes. So basically we tried to kind of aggregate our first order concepts based on our shared understanding then. And this is how we ended up with those second order themes. And then we conducted another workshop in order to kind of also align this understanding. And based on our second order themes, we then derived third order dimensions or aggregated dimensions. And those aggregated dimensions more or less build the basis of elements for also our project, namely machine learning based teaching system. Okay, cool. So that was more or less the theory behind it. So the methodology that we went along and got inspired from in order to basically kind of come up with a thorough research for machine learning based teaching system. And now I actually want to go ahead and show to you and explain to you how machine learning-based teaching systems are set up, what are core elements to those. So basically, present to you our findings and results. So what you can see here on the slide is basically the framework of machine learning-based teaching systems. And in the beginning, it might be a little overwhelming because we have so many different elements. We have so many different entities that are super important that are displayed here on the right-hand side. So we have the organization, we have data, we have teaching, we have knowledge. So I'm trying to guide you now through those different entities and try to highlight those dimensions, those aggregated dimensions that we came across and that we synthesized when we analyzed the literature. So I want to start with the entity of organization. And the first dimension that I want to dig deeper into are design strategies for machine learning-based teaching systems. And in the end, you will see that all of them somehow are linked with each other. But design strategies for machine learning-based teaching systems are the first one. And those are, well, this is basically the element that connects a machine learning-based teaching system within the organization that it is set up. So those machine learning or those design strategies kind of are like the underlying pattern that designers of such systems use in order to develop those and design those. So what is really important, or what we found out, which elements they are basically depending on, is first of all the task domain. So when we kind of digged ourselves deeper into those papers, we realized, okay, those teaching systems are basically set up in so many different contexts. We came across use cases where they were used in order to basically steer some huge machines. You got haptic feedback. They were also used in order to teach people like specific tasks, for example, differentiating bird species from each other, or kind of like becoming or training medical novices in order to improve the understanding of, let's say, cancer cells on mammography images and so on. So the task domains kind of informs those designers how to set up machine learning-based teaching systems, in what kind of domain they have to focus it on. And of course, also the machine learning model that is being used, that is basically underlying within the machine learning teacher, is also informing the designer, as we kind of have to figure out, okay, for example, do we want to use a large language model? Do we want to use a computer vision model, and so on? So basically on the capabilities those machine learning models bring along, we kind of have to link it to the task domain, so we can, so a designer can actually develop such systems accordingly to the requirements within the organization. So the other entity that is then super important, and that is basically also linking then the organization with those machine learning based teaching systems, is data. So we have two different kinds of data that we want to distinguish. You might think, okay, well, it's kind of obvious. We have the data that normally machine learning models are trained on, or that even XAI models are trained on, but it's a little bit more complex because we have to differentiate here between domain representing data. So basically the data, for example, that is used in order to, let's say, kind of map all the past decisions an expert did in a specific domain. If we think of that mammography example, it would be basically the past decisions a medical expert did in the past, or a surgeon did when they were trying to figure out whether we can see cancer cells on a mammography image or not. And this data is then normally used in order to also train a machine learning model. But then on the other side, we also have novice representing data. And as there are so many different kinds of machine learning systems out there, this could be presented in different ways. So what we mean with novice representing data is basically how a novice is articulating, for example, its state of learning. So a novice can give feedback to a teacher based on indicating, let's say, on images, what so far which kind of concept he didn't understand, or based on text, which kind of text concepts were not understood, and so on. So we are normally differentiating between domain and novice representing data. And then we have the teaching aspect itself. And the teaching aspect is maybe like one of the most, I mean, they're all important, but for the presentation here, the most important one is here, especially the role of explainable AI comes into play. So on the left-hand side, you see also this element of this aggregated dimension machine learning training interaction mechanisms. So this is basically the way how we train our machine learning based teacher. So how we train our machine learning model. This can be based on domain representing data, so we can do it in a supervised way. We can also like have data that is, let's say, not labeled. We can have a subject matter expert kind of supervising this process, where we're going a little bit more into this semi-supervised direction. So basically, with this element or with this dimension, we actually try to synthesize. Okay, or this is what we found out, how all those systems that are out there are synthesizing this this transfer from subject matter expert to the machine learning model. But then on the other side, and this is the other important one, is the machine learning based teaching interaction mechanism. So this is the way how the machine learning based teaching system is interacting with the novice. So basically, in which kind of feedback loops is this concept incorporated? Is the novice able to give feedback? Is the machine learning based teacher to kind of also like apply some explanations, some instructions on top of, for example, examples that are provided to the novice? So let me just give you an example. So it's not, this part is not so theoretical. I will also show you some real world examples later on. But it could, for example, be the case of machine teaching. So in machine teaching, we're trying to come up, or is this concept where we're trying to come up with samples that we provide to a learner. And the samples should be set in such an optimal way that the novice is learning as fast as possible. And here we could also differentiate between a novice that is not necessarily a human, could also be a machine. But if we stay in this concept where we're looking at humans, the machine learning based teacher could provide those kind of examples to the human learner, and then on top also provide explanation. And this is then basically leading to also those teaching reflection mechanisms. So basically a novice has then also, of course, the option to kind of reflect on what is being provided, what kind of information is being provided to the novice. Is it like some kind of Lime statistics? Do we get like counterfactual examples provided on top? Is it like argument based? This is also one of those niche fields that we stepped into. There are a lot of systems set up where they're kind of trying to provide on top some argumentation. So basically some kind of reasoning concepts to the novice. So this learning procedure is being enhanced by a lot. And I will dig deeper into this right-hand side and kind of elaborate what the role of explainable AI can be in this context in just a second. But beforehand, I also want to mention the last entity that we came across, and this is knowledge. So within knowledge, basically, we're looking into, okay, in the beginning, I was kind of highlighting it from this perspective where we have this direct and indirect knowledge transfer. But what we understood is when we went through the literature, that there are several knowledge transfers taking place, and you can sum them up as two, from the expert to the machine learning based teacher, and then again back to the novice. And all of them are basically making use of the task specific knowledge that is, of course, also linked again to the task domain. So basically the task domain that we see up there in the organization. And this is basically how all the different dimensions that we came across. So in total, we came across 5 dimensions. This is the design strategies for machine learning based teaching systems. We have the machine learning training interaction mechanisms. We have the machine learning based teaching interaction mechanisms. We have basic elements of machine teaching systems. Those are basically represented by single elements within this graph, within this figure. And then we also having those teaching reflection mechanisms. Okay, so this is more or less the theory behind machine learning based teaching systems. So now I want to go a little bit deeper into, okay, how, or focus a little bit more on this dimension, machine learning-based teaching interaction mechanisms, because here the role of explainable AI comes into play. So beforehand, I was giving one example of machine teaching as one kind of concept that we came across when we try to understand machine learning-based teaching. And I just quickly want to recap what kind of possibilities are out there and how explanations and this interpretability aspect is and why this is so important. So earlier I was already mentioning that within machine teaching, we have a teacher and a learner. And what we conventionally would do is we have kind of passive learning. So we just provide a training set to our learner. And then this learner is more or less trained on this training set. Then, of course, we also have active learning where the learner can kind of query samples, for example, of high uncertainty. But then we have this aspect of machine teaching. And in machine teaching, we have machine teaching and iterative machine teaching. The difference is in machine teaching, we kind of try to construct a training set that we provide to a learner. And then the learner can give us back information like, okay, the current state, or like highlights on images, for example, or in text, or in regression analysis, kind of highlight examples that the learner didn't get along well. And then we can kind of optimize this training set. But what is happening in iterative machine teaching is we can kind of provide samples to the learner. And then the learner for each sample can iteratively provide information back. And when those examples are being provided to the learner, they can be facilitated with explanation based on XAI. And such explanations, I want to highlight one example. That is a paper from Goyal that he presented at ICML in 2019, where he basically came up with the concept of counterfactual visual explanations. Most of you might be already familiar with it, with the concept, but I just quickly want to highlight what's going on, because what they already showed in their paper is that when you kind of utilize such examples that you provide to a learner, and you add them, or you kind of like add explanations onto those examples, the learner is even improving his performance on task. And this kind of sets the path towards how we can then in the end make use of such machine learning based teaching systems in order to set them up in organizations to kind of improve those learning processes. So how it is set up is basically we have a query image. The query image basically is the image that we try to kind of show to the human learner. In this case, we're looking at I think it's Chinese figures, and then we have a distractor image. The distractor image is normally an image of a different class. And what we're trying to, or the basic idea behind this is, it is that we kind of look at discriminative areas. I will just in a second explain what those discriminative areas are. And based on those features in both images, we kind of create a new image that in this case is called the composite image. And we basically combine the two features of those discriminative areas that show kind of the difference when we take the right area and add it to the left area to kind of highlight, okay, if we would use the most important features of the distractor image and put them on the query image, it would look like this. And those discriminative areas are based on the areas of the AI that would confuse the AI system in the end. So meaning, if we would swap now, like we did in the composite image, the two areas, the AI system would actually come up with a wrong prediction. And this is basically being used as kind of like thinking, okay, apparently this area in the image is super important in order to differentiate between the two classes. So if we swap them, then we can kind of highlight to our learner which areas in the image are important to differentiate the two classes. So basically to come up with the decision boundary, kind of in this way, visually highlight this decision boundary. So the learner understands in a more advanced way which areas he or she has to focus on in order to come up with the right solution for a given task. So basically, in this case, we would then use it in order to teach someone a specific language or specific digits in a specific language and so on. So this was now an example how we can utilize XAI in order to kind of facilitate those learning processes. And what we then did in the end of the paper, we tried to come up, okay, now we understood really important elements of such machine learning based teaching systems. But what are actually now, what is a research agenda that we can focus on in the future in order to kind of utilize that now also for practice? So we came up with different research avenues, and in this I want to highlight 3 of them. If you want to check out the paper, there you find 7 more. So what we came across is that previous research already shows that XAI can be used to provide feedback to learners, and this is supposed to facilitate the learning process. But then we also came across that human factors, or the human learner, him or herself, plays a really important role in this. So it is super important to understand like the different human traits or how different human traits can affect this learning process, and also the ability to learn when they are being taught in such a way. And obviously also then how the different stimuli of explanations by XAI can or do affect this learning behavior, learning performance of humans. So an example would be if we, for example, compare the cognitive styles of humans. Some might be more affine in visual explanations. Some might process textual information better. We would kind of like compare, and this is actually one of the projects that we're conducting right now, kind of look at how does this cognitive style affect now different kinds of explanations that we provide to humans. So let's say when we provide them text explanations or natural language explanations or counterfactual explanations, example-based explanations, how does this actually affect the learning process of humans? Then we also came across, and that was what I was already highlighting, that task-specific knowledge is basically a really important element within such teaching systems. And so far, most of the research that is focusing on such teaching systems and is utilizing explainable AI is mainly focusing on computer vision tasks. And one important research avenue is, of course, to kind of also scrutinize, okay, what kind of other research avenue, what kind of other explainability methods can be used in order to also train humans on different domains. So basically, for example, use different kinds of explanation modalities, maybe also combine them in order to be able not just to teach them computer vision tasks, but let's say also regression tasks, text-based tasks, and so on. And then a last future research avenue that I want to focus on is basically the communication style between the machine learning-based teacher and the learner. Because the communication style, so basically the way how it is being communicated, you could think of like, okay, I'm providing examples to the human learner, but on top, when I provide the explanations, I could, for example, provide assertive explanations. I could provide unassertive explanations. There are already like studies out there that dig deeper into this, and they found out that this communication style is super important. So in order to enhance now the learning performance of humans, it is really important to understand how such communication styles affect the learning performance of humans in order to kind of develop and also provide guidelines to designers of such systems to make them more effective in the future. So with this, I already want to come to the end of the talk. So basically, what we did in our project was to conceptualize, based on previous literature, what machine learning based teaching systems actually are, to kind of build an understanding how they are set up, and to also provide a framework that can guide as as kind of also like guidelines for future research and practice to dig deeper into those topics, and based then on our research agenda to kind of highlight paths that are worth to dive deeper into. But of course, we also have to talk about limitations. So first of all, I want to mention that all the research avenues that we came up with are based on theoretical foundations. So far, of course, they lack kind of empirical evidence. So we kind of also want to invite other researchers and scholars to participate in this kind of endeavor, and also like start conducting more empirical evidence. And of course, in the literature analysis that we did, there's always room for human error. So of course, it could be that we, for example, left out one or two articles just because we didn't come across them, or they were not linked to all the articles that we read through. And overall, all the research avenues that we set up kind of build a really nice research agenda that is worth looking at. So in order to also kind of make use and scrutinize the use of explainable AI to transfer this expert knowledge. And also we want to kind of invite researchers to broaden the scopus, because so far it's been focused in narrow domains. So how can we use explainable AI also to facilitate this human learning in other domains? Cool. And yeah, with this, I would like to thank you a lot for your attention. If you have any questions or recommendations or feedback, I'm gladly here to discuss with you those. And yeah, if you're interested in the paper, here's a QR code to check it out.